So for those of you who are joining us after the fact, welcome to the Year 9 Higher webinar. We're going to be looking at an introduction to electricity, but we're just recapping what we did last week. Those of you who are here currently, voting, see if you can remember which of these are reliable. Let's have a look at what you've said. So nuclear is reliable, it absolutely is. Some of you think biomass is reliable. Well, you are correct, those 54% of you. Fossil fuels are, geothermal is, good job, and hydroelectric is as well. The ones that aren't are the ones that you can't rely on them all the time. You can't always rely on there being waves, you can't always rely on it being sunny, particularly at night. You can't always rely on the tide moving a large volume of water. That only happens in between the tides, not at high and low tide, and you can't always rely on the wind. Okay. Good job, well done guys. So what we're going to be looking at today is an introduction to electricity. Now, a lot of this might be familiar to you if you covered it in Year 7 or Year 8, but we're going to assume that you've forgotten it, and I'm going to go right back to the start and try and explain everything through. So here's from the tick list, the things we're going to be doing, and hopefully we should be able to fit all this in. Now, there's a good chance you'll have questions, so remember, if you have a question, do ask Ms. Wanstall in the chat, those of you who are watching live. So the first thing you need to remember is about drawing circuits. Now, I'm not going to spend loads of time on this, but on one side, you've got all of the circuit diagrams that you need to know. These are the symbols. I'm not going to explain what all of them do. We're going to touch on some of them today, but not all of them. The ones that I really wanted to pick out were cell and battery. So in the diagram for a cell, the long line is the positive side of the cell and the short line is the negative. So when you connect them up, you can see it's got positive, negative, positive, negative. If you connected that the other way round with a short line there and the long line there, that would be like connecting batteries the wrong way round. So it wouldn't work in the appliance you're trying to power. They would be working against each other. One would be trying to push the current around one way, the other's trying to push it around the other way. You've got to connect them up the right way around in your remote control. You've also got to draw them the right way around here. The difference between a cell and a battery, now this is where it gets annoying, because if I say battery, you're clearly thinking of the kind of thing you put into a remote control. But in science, one of those things is called a cell. And when you get multiple cells together, that's a battery. So one Duracell battery, Duracell, that's where that cell bit comes from, is a cell in science, not a battery, because a battery in science is multiple cells put together. On the other side, I've put an example of an exam question. This is 2 marks in a GCSE exam for just knowing these symbols and drawing them. So I'm not going to spend ages talking about them. There they are. You just got to learn them. So there's only about 15 of them. So this is great flashcard fodder. Put a symbol on one side and the name of it on another. Test yourself both ways around. Can I recognize what that symbol is? Can I remember what the symbol is from the name? So do it both ways around. They make brilliant flashcards. We're going to be using those a little bit today, and there are some exam questions which use circuit diagrams, so you will need to know these, but I'm just drawing your attention to them, but moving on pretty quickly. Okay, back to basics, back to a bit of chemistry. Structure of an atom. So here's an atom, and we've got the nucleus with the protons and the neutrons and the positive charge in the center, and we've got the negatively charged electrons on the outside. Now, the reason I've picked up on this is to go back to recap the idea of charge. Electricity is all about charge, but charge is measuring how negative or positive something is. If something's got the same amount of negative as positive, that's the same amount of charge, but one's a positive charge, one's a negative charge. So you can have different amounts of charge. Electrons, we often say, have got a charge of -1. That's, if you're talking in chemistry, that's absolutely right. In physics, they've got a charge of 0.000000, go on for quite a while, and then I think it's a 6. They've got a really tiny amount of charge on each electron. You need trillions of electrons to have any substantial amount of charge. But atoms are so tiny, that's quite possible. So in chemistry, you're used to this having this sort of chargeless -1 +1 kind of state, or a 2+ ion, for example. But in physics, we want to talk about lots of charge altogether, and we measure it in something called coulombs, named after a French scientist. So charge is this inherent negativeness or positiveness. And that links to electricity because electricity is the flow of charge through a material. Normally that's electrons, and normally they're flowing through metal, but there's lots of other things that can happen. For example, your nerves, it's not electrons that are flowing, it's hydrogen ions, it's protons. So the electricity that powers your nerves is not electrons moving, it's actually protons moving, positive ions, hydrogen ions as a proton. Don't need to know about that really until A level, but just to make you aware, there are more kind of things that can flow than just electrons. You might remember in chemistry some electrolysis, we had ions flowing. That's still electricity because it's a charged particle moving. But most of the time in physics, we're going to be thinking about electrons flowing through wires. That's where the bulk of our electricity that we are going to deal with is. The first big idea is the idea of current. And the current is how quickly is charge flowing? That's kind of the basic idea. How much charge flows in a set amount of time? So imagine that I'm inside a wire and I'm counting these electrons go past. You know, there's 1 coulomb of charge, there's a 2nd coulomb of charge, there's a 3rd coulomb of charge flowing past me. It's how much charge flows per second. It's the rate of flow of charge. So current is just charge flowing. The size of the current is the rate of flow, how much charge per second. Now there's 3 equations we're going to be covering in this, and all 3 of these equations you are going to have to learn. I mentioned flashcards for the circuit symbols. Again, these equations are brilliant for flashcards. So again, I know some of you out there love flashcards. Making your own flashcards now, while you've got the time at home, is a really good idea, and you're going to thank yourself when it comes to year 11 and you've got this stack of flashcards ready for you to revise from. So I'll just talk through these, so I don't know how many of you have dealt with this kind of stuff, and just a reminder for some of you who've done it before. Here is the equation. The charge is the current times the time. But in science, we sometimes like to be a little bit lazy, and we use just a single letter instead of a whole word. So Q equals I times T is the same as charge equals current times time. We're using Q for charge. Now that's a little bit confusing, because why not use C for charge? It starts with C. Well, current starts with C as well. Why not use C for current? In fact, we use C for something else entirely. We use it for capacitance and the speed of light. So it's already been taken, so we needed other letters. Exactly why they chose Q for charge and I for current, I don't know, I'm afraid. Luckily, T is an easy one. T for time, that one checks out, that one makes sense. Now you'll notice in this triangle, which we'll come to in a second, that it's got a C there, that's the unit. Charge, the letter for charge when you're writing out an equation is Q, but it's measured in coulombs, and rather than writing coulombs, we just use a capital C. A bit like for seconds, we use an S, but for coulombs, we use a capital C. So that capital C in the triangle is about the unit of charge. Current, the letter we use for the equations for current is an I, and that's measured in amps, and the letter we use for the short for amps is A. So that's just a reminder that this summed up here. And here's a triangle. Now, just to remind you how these work, the way I like to, first I'll talk about how to use them, and then I'll talk about how to build them. So the way these work is you cover up the thing you want to find out. So let's imagine I want to find out, I've got a calculation question and it's asking me to calculate how much charge has flowed, and it's given me a current and a time. What I do is I cover up the thing I want to find out. And what I'm left with in the rest of the triangle is the equation I want to use. Now here, I've already got it. Charge is current times time, and that's exactly what's come out of here. By covering up charge, I get current times time. If, however, I wanted to work out current, cover up the current, and I get charge flow in coulombs divided by, the fact this is over the time, it's literally charge flow over time. That's another way of saying charge flow divided by time. That will give me the current in amps, so long as my charge is in coulombs and my time is in seconds. And finally, if I wanted to work out the time, if they gave me a charge flow and a current, said, well, how long has that current been flowing? I would do charge flow over current, charge flow divided by current. So definition, 1 amp is the current that flows when 1 coulomb of charge passes a point in a circuit in 1 second. And 1 divided by 1, that's 1. So Hopefully you've got a calculator nearby. That could be on your phone. Maybe you're going to switch over to like Google to get a calculator. But here is a simple calculation I'd like you to have a go at. If 36 coulombs of charge flows in 9 seconds, how much current has it got? So I've got a little poll for you. Grab your calculators. You've got 4 options. If 36 coulombs of charge flows in 9 seconds, how much current is there?
Hello, sir. Could you possibly move the poll a little so we can see the actual numbers of the question?
Like that?
So, if you drag
the poll. Oh, no, that's the wrong.
the actual question bit. Oh, I think I can move it.
Yeah, you should be able to move your own poll. Sorry, I've set you the wrong one. I wanted to set you that one. Sorry, I set you the harder question first. That's wrong. So I've reset that poll with the actual numbers from this question. If your poll is covering up your numbers, then you can move it yourself. But if 36 coulombs of charge flows in 9 seconds, what's the current? So you've got we're trying to find the current, cover up the current, remember? You should then be able to work out the equation you need to use to figure out a current given this triangle. And I can see, good, loads of you have had a go at this. Well done. Some of you have multiplied them together, only a few of you. Most of you have taken 36 and divided it by 9. Now, if I was writing this out, I would start with my equation, Q equals IT. Then I would use my triangle to rearrange it. The current is the charge divided by the time, Q divided by T. Then I'm going to substitute in the numbers. So my charge is 36 coulombs, in it goes. My time is 9 seconds, in it goes. 36 divided by 9 gives me 4 amps. Hopefully you found that one quite simple. I've got a slightly trickier one I want you to have a go at, so don't put that calculator away. How much charge flows in 2 minutes with a current of 12 amps? So here's another poll for you. Which I will share with you, but hopefully you're busy on your calculators already. Relaunch that poll. So 2 minutes, 12 amps, how much charge? Now, in the exam, this would probably be a 2 or a 3 mark question, whereas the first one might only be a 1 or a 2 mark question. And there is a reason for that, which I'll talk about in a second. Hopefully, some of you have already spotted it. Let's have a look. Okay, so we've got a split here. Well done. Most of you have done the right calculation, but some of you have done it a little bit wrong, and I'll talk about how that is and why that is. But well done. Currently at the minute, 60% of you have got it right. I'm going to end it there and just share in case you can't see my screen. But what we've got going on here is the time has got to be in seconds. This is what I call a heffalump trap. Any of you who've read Winnie the Pooh, Pooh goes and digs a big hole and puts some leaves over it and tries to get heffalump to come along and fall into it. The exam board do the exact same thing for you. You are the heffalumps they are trying to catch. Don't be a heffalump, spot the trap and don't fall into it. The trap here is they've given you the time in minutes, or I have, whereas for this equation to work, the time's got to be in seconds. So the first thing you should do is convert minutes into seconds, then put it into your equation. 12 times 120 gives you 1,440 coulombs of charge. Like I said, loads of you managed to spot that already. Well done. If you didn't, watch out. Don't be a heffalump. Okay. In a circuit though, here's a diagram of a circuit. Sometimes you want to measure the current and see how much current is flowing. Now, my analogy I'm going to use here is thinking about electricity a bit like water. We're going to get deeper into more different analogies and models next week when we do a bit more on electricity. But for now, think of electricity and charge flowing like water flowing down a river. Now, I can't tell just by looking at it, is this a fast flowing river or is this a slow meandering river? The water going through it is like my charge flowing through my circuit. But how fast is it going? Now, just standing on the side of the bank, I can't tell just by looking at it. I've got to, maybe I'm going to throw a stick in there and see how quickly the stick goes down the river. Maybe I'm going to put a little windmill type thing, little propeller in there and see how fast it spins, and I'll be able to get an idea. The faster it's flowing, the faster it's spinning. But either way, if I want to know how fast the water's going, I've got to get something in the water. It's got to take part in the water, and hopefully by being there it's not going to slow it down too much, because otherwise by measuring it I'll be changing it. But I'm going to try and get an idea of how fast it's flowing, how much water per second, or in our case for electricity, how much charge per second. So I'm going to put something in it. In the same way, if I have this circuit, I need to make the ammeter, this box that measures current, I've got to make it part of the circuit. So this is one big loop, and here's my ammeter, which is telling me I've got a current of 4 amps. So ammeters are always connected as part of a big loop to measure, and it doesn't matter where you put them in that loop, it should be the same all the way around that flow. We'll talk about that more next week. But ammeters have to be connected in series as part of the loop. Now, I'll give you the contrast of that a bit later when we look at voltmeters, because voltmeters are different, but ammeters always connected in series so we can measure the current that is flowing through the wires. Let's move on now to potential difference. Now, you might have heard potential difference, but you've almost certainly heard of voltage. They are exactly the same. You can use voltage in your answers and you will get full marks for that in the exam. That is absolutely fine. But the questions will always say potential difference. So they're the same thing. Potential difference is what the exam board uses and what a lot of scientists will use. Voltage means exactly the same thing. You can use either. It doesn't make a difference. Okay. Now this diagram, I think this sums up basically what we're talking about in the whole of today. So this green person here, this is the current. What we're interested in is how quickly can this current flow through this tunnel here? And the answer is going to depend on a couple of factors. One, how hard is that person in yellow pushing them? The harder they get pushed, the faster they're going to go. That makes sense, right? The other one is how much is this red person trying to stop them? By pulling them, they're slowing them down. The harder they pull, the slower the green guy's going to go. The yellow represents potential difference or voltage. The red represents something called resistance, we're going to come on to in a minute, but we're going to come back to this same diagram. So let's just focus on the yellow person for a minute. What we said is the harder they push, the faster the green thing, the current, is going to go. Well, there's not a physical force exactly, but what you have is an amount of energy. So think about how much energy this person is using. The more energy they've got, the faster the green person's going to go, because they're going to be able to push them harder because they've got more energy. What potential difference is a measure of how much energy is supplied to each unit of charge, to each coulomb of charge. So 1 volt of potential difference is 1 joule per coulomb of charge. Again, we've got an equation. This is another equation you need to learn. But again, this is something that will go really well on a flashcard. So flashcards for these equations, really good idea. The amount of energy transferred is equal to the charge flow times the potential difference. Here's another one of those triangles, this time just using the letter. So again, if I wanted to know the charge, amount of charge, and I was given an amount of energy and a potential difference, a voltage, to cover up the thing you want to find out, and I would do the energy divided by the voltage, the potential difference. That's got to be in joules for energy. It's got to be in volts for potential difference, and it's got to be in coulombs for charge. So again, here's that same idea. I've got another calculation I want you to do. 5 coulombs of charge is given a total of 45 joules of energy. Calculate the potential difference. So yet another poll.
Hello, sir. Could they possibly have a little bit longer on this one?
Sure, no problem. I'll give you about 2 minutes.
Thank you, sir.
So, no, that's not the one I want. Wrong poll, apologies. Ah. There we go, that's the one I want. So I'll move this so you can see. Here's the triangle you need to use. It's asking you to calculate the potential difference. None of those start with P. Trickier. But we have got energy, that starts with E, that's an easy one. So, No Heffalump traps in this one. That charge is in coulombs, the energy is in joules, it's all fine. We don't have any conversion we need to do. In the one, I've got another one after this. I want you to have a look carefully at the one after this because there may be some Heffalump traps. Quite a lot of you fell into my Heffalump trap last time. I don't want any Heffalumps this time if we can avoid it. So let's have a look. Okay, still a few of you I'm waiting for, but lots of you are getting your heads around this. Well done. This one was a bit easier. This is kind of the level 2 kind of question. They're sort of the earlier in the higher tier paper, they might give you one like this. For those of you wanting to get 4s, 5s, this is the one you should definitely be getting right. Those of you aiming even higher, you should be finding this easy. Okay, let's have a look. A little bit longer for you. So let's see. Good job. 89% of you getting that right. Well done. And just a few of you. So someone has divided it the wrong way round. You needed to get the energy is 45, the charge is 5. So you do 45 joules divided by 5 coulombs is 9 volts. When you're writing out these exam questions, it's always a good idea to show you're working. If you make a mistake putting numbers into your calculator, I've seen that happen so many times to bright students, just press a minus instead of a plus or a multiply, or a minus instead of a divide, and the wrong number comes out. If they don't write the workings, they get no marks. If you get the right workings, you've written all of this, and then suddenly this comes out to 40 because you did minus instead of divide, you still get some of the marks for getting to this stage. I know it feels like, well, it's obvious. It's just a safety net for yourself, okay? So a slightly harder one. I'm not going to read this one out, but I will warn you, this one has Heffalump traps. Oh, stop that. So have a look at this one. Have a go. Figure out the equation. Try and figure out the numbers. This is very much the kind of question that you would get towards the end of the paper where they are trying to separate out those people who are going to get higher grades. Having said that, you can still fall into the Heffalump trap and get most of the marks, but I want you to get all of the marks. Okay, only 9 voted so far. Give the rest of you just a little bit longer. This one is harder. Okay, right. It's a minute and a half. Well done. Got quite a lot of people voted, so thank you. I'll leave that poll open just a little bit longer as we start to talk about what's going on here. The Hefflamp trap here is the units. Yes, that's in volts and that's in joules, but they've got these prefixes to them, these kilo, mega, giga. And you need to be aware of what these prefixes mean. This is not 10 volts, this is 10 megavolts. Now, some of you might know from computing, maybe is where this comes up a lot, or from mobile phone packages about data, about megabytes and gigabytes and terabytes and things like that. There are 1,000 bytes in a kilobyte, or 1,000 grams in a kilogram. There are 1,000 kilobytes in a megabyte. So 1,000 times 1,000, that 10 megavolts is 10 million volts. So M for mega, M for million, that one works out quite nicely. What about giga then? Well, how many megabytes are in a gigabyte? Again, it's 1,000. So that's another 1,000 times higher. So 10 megavolts is 10 times 10 to the power 6 volts, 10 million volts. 1 gigajoule is 1 times 10 to the 9, a billion joules. So when you're putting that into your calculator, that billion divided by 10 million. Now, some of you might have scientific calculators and you might be happy putting in 1 times 10 to the 9 divided by 10 times 10 to the 6. If you're happy doing that, great, that's absolutely fine. You can do it that way, or you can type out the number. Either way, you come to an answer of 100 coulombs, which only 7, oh, now somebody's just clicked in because they've heard me tell them the answer. Well done. 7 of you got it right. Maybe I'm being harsh. Maybe that 8th person also got it right. Some of you choosing 10, what you may have done is just done 10 divided by 1. 10 is the first number, 1 is the second number. I'm going to divide them, or 10 times 1. You've got to make sure you're looking at your equation and getting it the right way round. It's E over V. Now, it gives you the voltage, the potential difference first, and the energy second. So you've got to think, well, maybe they're not going into my calculation in that order. It wants the energy divided by the potential difference. So 1 gigajoule, 1 billion joules, divided by 10 million volts gives you 100 coulombs of charge. Well done to those of you who had a good go at that. Well done if you spotted the Hefflamp trap and tried not to fall into it. In the exam, this would probably be worth 3 marks. If you ignore it and go, well, I'm going to do 1 divided by 10 and come up with 0.1, you'd get 2 marks for that out of 3, because you've done the equation right. You just ignored the Hefflamp trap. So you're still getting some of the marks, but you're not getting all of the marks. And I and your teachers want you to get all of the marks in these kinds of questions. Okay, so we've looked at current, we've looked at voltage. Next, voltage gets measured by a voltmeter. And voltmeters get connected in parallel. And here's how I'm going to try and explain that by using another analogy, which again, we're going to come back to next week, is imagining that energy, if the current is like the water flowing in the river, the energy is like money. So you've gone to the cell, your parents, and they've given you £50. Great, you come out from your parents and you go to the shops, which are now open, and you can go and buy things. Here is you about to go into the shop, and I stop you and go, can you tell me how much money you've got in your pocket? And you go, oh, I've got £50 in my pocket. I got given that by my parents. You go, all right, good job, okay. And then after you come out of the shop, I stop you again and go, how much money have you got in your pocket now? And you say, well, I've got £30 in my pocket now. Then I can go, well, that's easy. You came in with 50, you left with 30. I can work out the difference in how much energy you've got, in how much money you've got. And energy is sometimes referred to as potential, gravitational potential energy, chemical potential energy. Energy is potential. I can work out the difference in your potential before you went into the shop and after you came out. Now, why don't I just go into the shop and see what you're buying? Well, in an electrical circuit, the shop is representing this bulb here. Now, we can't put a little meter inside the bulb to see what's going on. So instead, we've got to have a look at the electricity before it gets into the bulb and after it comes out of the bulb, and look at the difference. So you can see here is a series circuit. Here is that loop we talked about, which has got my battery, 2 cells put together, my ammeter, and my filament bulb. The ammeter is in series. It's part of that loop, so it can get inside and see how fast the current is flowing at that point in the circuit. But the voltmeter has got an extra branch, an extra loop added on, so that it can measure the amount of energy per unit of charge before it goes through the bulb and the amount of energy per unit of charge after it comes out, and work out the difference for you. So voltmeters measure voltage, you connect them in parallel. Ammeters measure current, and you connect them in series. Great. Let's move on to our third topic, which is resistance. So if you remember this picture, it's this red person at the top. Now, the simple idea for resistance is the more resistance you have, the harder he's pulling, the slower the current's going to go. So it doesn't directly interact with voltage, but these two together determine the current. If he's pulling twice as hard, they're going to be going half the speed. If they're not pulling very hard at all, they're going to be going much faster. So resistance slows down current. The more resistance you have, the slower the current is flowing. And resistance is measured in ohms. And because scientists are hilarious, they thought, what symbol can we give this thing named after this scientist called Ohm, who did a whole load of science on electricity? Oh, I know, let's use, you'll like this, the Greek letter omega. You see what they did there? It's really not very funny. But this funny sort of squiggly symbol is the Greek letter omega, and that is the symbol we use for ohms. So like we had V for volts and A for amps, omega ohms. What causes resistance? So remember from your metallic bonding, metals have these positive ions with these delocalized electrons. And in electricity, these are flowing past these positive ions. They're being pushed around by this energy, by this potential difference, pushing them around the circuit. As they push round, they collide with these fixed positive ions. And the more they collide, the more they're going to get slowed down. So the more collisions, the slower the current. That's what resistance is. It's really the negatively charged electrons colliding with those positive ions. This is all summed up in something called Ohm's Law. And what we were just talking about ties back to this picture. More potential difference, faster current. More resistance, slower current. Or when you actually quantify it, if I double the potential difference, I'll get double the current. If I double the resistance, I'll get half the current. There is a numerical link between these three things, and it's summed up by, I'm afraid, your third equation you have to learn. So this is linking V for potential difference, voltage, I for current, and R for resistance. So again, here's a triangle, and you can see for any one of them, you can use the triangle to rearrange to produce a number, which you can then calculate. So Ohm's law is fundamentally, it's this relationship between voltage, current, and resistance. If I have double the current, double the potential difference, I get double the current. If I have double the resistance, I get half the current. Now, we'll come on to some phrases for those in a minute, but one thing to point out, and we're going to go into more detail about this next week, so you might be asking, oh, why is that? I want to know. We will explain, but next week when it becomes relevant to something else we're going to talk about. This is only true for wires, components, things in an electrical circuit that are at the same temperature. If you change the temperature of a thing, it can change the amount of resistance. And some of you might already be making connections and figuring out why. If you're still puzzled, just wait for next week. We'll explain it and put it in context in a bit more detail next week.
Hi, sir. Can we just cover what I means?
Sorry, a reminder, I is current. So back here, I is the symbol that we use for current because I don't know why I is current. Remember, Q is charge, I is current. This is the same I as we're using later. So V is for potential difference, I is for current, R is for resistance, measured in volts, and amperes is the long word, but saying amps is fine, and ohms for resistance. I've got all of that on a summary slide at the end, all of those things I've just said, as well as all of the three equations and the parallel and series for the measuring devices. Right, Running low on time, so I'm going to do this quickly, but this is hard. And there is one of the questions you might be set this week involves this idea. If we draw a graph of voltage against current, now why is it that way round? It's because typically voltage is the independent variable which goes on the x-axis. By increasing the voltage, you increase the current. This affects this. This is the dependent. So this is the independent. The current is the dependent. You can work out the gradient of a line like that by doing rise over run, and the gradient gives you an indication of the resistance. Now, actually, because that's V and that's I, the gradient is the inverse of the resistance. 1 over the gradient is what you need to get the resistance. So you can see 1 over R equals change in I divided by change in V. So for resistance on this graph, it's actually run over rise, but that's a weird thing. Normally gradients are rise over run. So don't worry too much about that, but that will be important when we come to in one of your questions, because there is a graph question where you have to calculate the resistance from a graph. Remember that it's 1 over the resistance. The gradient isn't the resistance. But you can just, another way of doing it is by working out your V and your I and putting it into this equation by reading it off the graph. By taking 2 points and going, right, how much does the potential difference increase? How much does the current increase? Not all devices obey Ohm's law. Not all devices do you get this nice straight line that goes through 0, 0. That's called being directly proportional. So another way of saying Ohm's law is that voltage is directly proportional to current. That's true for a lot of things, but there are things where the resistance is not constant. Here, because we've got a straight line, that gradient isn't changing. The gradient, remember, is an indication of the resistance. Because the gradient's not changing, the resistance isn't changing. But here, the gradient of the graph is changing, which means the resistance is changing. That means this is a non-ohmic device. It's not obeying Ohm's law. What if you've got something like this and they ask you to calculate a resistance? Well, on this one, it's easy. You just do a gradient and then do the inverse of the gradient, 1 over the gradient. But on this one, well, how do you do a gradient of a curve? What you need to do is draw a tangent. So I've zoomed in on this bit of this graph so you can see what's going on. And I've taken a gradient at about 0.6 volts. So the question would have said something like, calculate the resistance at 0.6 volts. So the first thing I've done this twice. One is right, one is not as right. I've drawn a line here where I think 0.6 is on my scale. That's the pinky line. And then I've tried to do a straight line that kisses at that point. Now, I think this first one I've done isn't particularly good, and I'll show you how I know that. Can you see if there's a triangle made by this red line and the black line of the graph itself? And what I'm looking for is, where is the white point of the triangle? Can you see this white area here, this white triangle? The point of that triangle is really close to my 0.6 mark. But on the other side, here's that same white triangle, and the corner of that white triangle is really far away. Can you see it's about there? That's a long way from my 0.6 line. What I want on a good tangent is where they're about the same distance. So you see that one, the white triangle starts there. That one, the white triangle starts there. They're about the same distance. This one is a much better tangent than this one. So when you're drawing your tangents, so firstly, mark up at what point. The question said, what was the resistance of 0.6 volts? That's 0.6 volts, and I've drawn a line up there. Now I'm going to draw a tangent to my curve that kisses it just at that point and look for those white triangles. How far away are they from that point where my original line crosses my 0.6 line? This one is much better. So having taken that one, I can now work out, here's how much my voltage increases. Here's how much my current increases, and I can do my change in voltage divided by my change in current will give me the resistance at that point. Now, those tangent questions, typically they are the harder questions in GCSE. Again, there is one that might require you to draw a tangent that your teachers might be setting you. I've produced a whole load of them. Your teachers will choose which ones they give you. You may need that skill. Okay, we've covered quite a lot, so here it is all in one slide. Potential difference is, the symbol is V and it's measured in volts, which annoyingly the symbol is also V. Current, the symbol for the equations is I. It's measured in amperes, but you can use amp, that's fine. And the symbol for amps is A. Resistance, the symbol is R. It's measured in ohms. The symbol is this Greek letter omega. Charge, the symbol for charge is Q. It's measured in coulombs, the symbol for which is C. Time is T, in seconds, S. Energy is E, measured in joules, capital J. Here are those three equation triangles that you need. And here is the ideas about the voltmeter and the ammeter. Ammeters being connected in series, voltmeters in parallel. Got a few minutes for some questions, so type them out to Miss Wanstall and I'll do my best to answer them.
Sir, I've got an answer.
Oh,
the conventional symbol for current is I, which originates from the French phrase intensity du courant, or current intensity, and the I symbol was used by André-Marie Ampère, whom the unit of electric current is named after.
So what you're telling me is I should blame the French?
Well, not, but the French person that came up with amps, there you go. Just answer.
Thank you, Miss. So any questions in the chat?
Which will be normally on the Monday, so you get a week to do the work that's linked with it, ready for the next webinar on the Tuesday.
Where we'll be doing more electricity.
And what is the work for the work? Do we have to answer the questions on the slides like we did in the polls?
No, because you've done those. Let me show you the kind of work that you will be asked to complete.
And I'm just going to put it out there for anyone in my class. I know you're struggling, but as long as you try, I don't mind. You know that. You're all awesome. I just want to verbalise it.
You will get set something that looks like this, which are exam questions asking you to have a go. Now, your teachers will talk to you about exactly what they want you to do, which questions they want you to focus on. Here is an example. Student used electrical circuits to investigate the relationship between resistance, potential difference, and current. Figure 1 shows how the student connects to the circuit he first set up. The circuit does not work. Explain what should be changed to make the circuit work. 2 marks. So here is a circuit, and there are 2 things at least wrong with it. How do I know there's 2 things wrong? Because there are 2 marks available. But looking at this, this doesn't look like the diagram that I showed you. You write your answer here to explain what you think is Watch out for Heffalump traps and watch out for looking to do a tangent. That is a difficult skill. Feel free to watch this video back again to try and help you with that.
Okay, sir. I just want to throw out slideshows for the webinar, and all the questions will be in your Google Classroom, along with a recording, which should be there by tomorrow because we have to download them. And so I just want to point out it's 1:45.
Perfect. I've seen that too. So thank you very much, guys, for coming. Any questions? Get on your Google Classroom.
Some questions, guys. Sorry.
What was that last one?
Do they need to do anything on the slides or complete exam questions? I was saying.
The exam questions is what your work is very likely to be. Look at your Google Classroom. Your teachers should make it really clear.
And I think that was it, sir. Thank you.
Good.
Sorry.
Thank you very much, guys. And we'll see you next week.
Bye.